Okay, good morning, everyone, or good afternoon for some of you. We're down to our last two lessons of optimization. So I'm only going to do one example today, so one video, and still optimization. We still have a constraint in optimization like we've done the last couple days. Um, the only difference here is this is going to be dealing with volume. For example, square boxes. Okay, how do we maximize or minimize the cost of material when you're building a square box, for example, okay? So again, I'm gonna do one example because I know these videos are kind of long and I don't wanna have you guys spend like 20, 25 minutes watching videos. I'm hoping that one example video will let you guys pause it, rewind it, and look back through it if you need help. But this one example video should be pretty similar to what you see on the three questions that you're gonna have on your assignment, okay? So again, you can print this out if you need to, or you can just write it out in your notes. It says a closed box with a square base is to have a volume of 250 cubic meters. Okay, so right away in that first sentence, it's telling us what our volume is, so we know that's probably going to be the constraint equation, is the volume. Okay, the material for the top and bottom of the box costs $2 per square meter, and the material for the sides, all the sides, costs $1 per square meter. Can the box be constructed for $300 or less? Okay, so let's consider cost our optimization, right? We're trying to get it minimal cost. Let's see if we can do it for under $300. Okay, so as usual, I usually just draw a picture just so I know what I'm looking at as far as top and bottom and dimensions. What's my X, what's my H? Okay, so here's my box. And let's call this an X, this is an X, and let's have a height of the box. We know that these are both the same variable because it says a square base. A square base has the same lengths on both sides, so X and X is okay. And that's actually what all of your practice problems are going to be like today, so you don't have to worry about anything else. Okay, so we have a constraint, and it looks like we're constrained by the volume. Okay, and then we have something that we're trying to optimize, which is cost. Same thing we did yesterday. If we're going to optimize cost, we have to see what is cost related to. Okay, yesterday we did a lot on perimeter because we were building fences and perimeters and whatnot. For today's example, when we're building boxes, the cost is related to the surface area of the box. So per square meter. So whenever you see square meters, that means it's going to be related to area. Okay, so let's set up our two equations. The volume of this box, if you guys remember from last week when we did box problems, it's going to be the area of the base times the height. So x squared h, x times h is going to give us our volume. And we're trying to optimize the area, which is going to be, let's see, we're building a closed box. So we have a top and a bottom. Let me just shade this in. There's the bottom, there's the top. Okay, so top and bottom is going to be x squared, right? X times x is going to give me the area of my base. But I have a bottom and a top, so there's two of them. Okay? And then I have to get the area of all my sides. So x times h would give me this side, but I have four sides, so it'd be plus 4xh, okay? And it looks like actually one thing I forgot to do here was to consider my cost. That's the most important thing. So the materials for the top and bottom are $2 per square meter. So top and bottom are right here. That's my surface area. I'm going to take that and multiply it by $2. Okay, so it's going to look like this. And then let's see, the materials for the sides cost $1 per square meter. So it would look like this. Okay, and that's going to give me my cost. Okay, so let's just, before we start taking derivatives and finding critical points or anything like that, let's just simplify this a little bit. So this will be 4x squared. This will be plus 4xh is equal to my cost. And let's look at our equation. We have what seems to be the odd variable out. We have an x, we have an x, we have an h. Looks like the h is the odd one out. So let's get h in terms of x. Okay, I'm just looking back at our problem here. Our volume had to be 250 cubic meters, so 250 equals x squared h. So 250 over x squared is equal to h. Okay? So let's just rewrite this. At 4x squared plus 4x, and instead of h, I'm going to write 250 x to the negative second is equal to my cost. And let's just simplify this so we don't have problems when we're taking derivatives. 4x squared plus 4 times 250 is going to be 1,000. Okay, this is x to the first. Remember when we're multiplying, we add our exponents, so 1 plus negative 2 is negative 1. Okay, equals our cost. We haven't taken a derivative yet at all. We're just plugging in our h and simplifying the equation. At this point, it looks clean enough that we can start taking derivatives and finding critical points. So let's figure out what our x dimensions have to be by taking the critical point, taking the derivative of this equation. So this would be 8x minus 1,000. This would be x to the negative 2, but I'm going to just say x to the 2. I'm going to put that at the bottom. Okay? Equals derivative of cost is 0, or derivative of c is 0. Okay? All right, so let's solve for x. Let's bring our 8x to the other side. So it'd be negative 1,000 x squared equals negative 8x. By the time you multiply both sides by x squared, you get, so if I just bring my 8 over to the other side, I'd have 1,000 over 8 equals x cubed, right? Because if I add x, these two exponents together, I get x cubed. Okay. So this, if I divide this by this, I'm going to get 125 equals x cubed. When you, whoops, not squared, cubed. When you take the cube root of both sides, you get x is equal to 5. Okay, so that's our x dimension. Let's double check and again make sure that we are at a minimum. We don't want to be finding a dimensions of a maximum cost. So I've got a little room over to the side here. Let's see, this was my original derivative. Okay, so we want to take double prime. So the second derivative would be 8. And then this would be, so this becomes, just so we're not lost here, this is going to be, this is the same thing as minus 1,000 x to the negative second. So when I take the second derivative of that, that would be plus 2,000 x to the negative third, or over x to the third. Okay, I took this negative 2, brought it out front, so that's what gave me positive 2,000. Okay, and then I subtracted 1 from here, be negative 3, which is the same thing as putting 3 in the denominator. If I were to take 5 and plug it in right here, I would still get a number that's greater than 0, which means we're concave up, which means we're at a minimum, which is good. It's telling me if I want to have a minimum cost, my x dimension needs to be 5, okay? So this would be 5, this would be 5. Let's figure out what our h would have to be. It'd be 250 divided by x squared is 25. It's going to be h, so 10 equals h. So that would be 10. Okay. So the question is, can the box be constructed for $300 or less? Okay. So if it's charging us $2 per square meter on the top and bottom, so on the bottom I've got, let's just write area of bottom is going to be 5 times 5 is 25. Okay. Area of the top, same thing, 5 times 5 is 25. And then area of all the sides is going to be, I'm going to write area of sides, is going to be 5 times 10 is 50. But there's 4 sides, so 50 times 4 is 200. okay? So the top and bottom together, there's 50 square meters of area, and there are $2 per square meter. So this is 2 times 50. And in the bottom, or I'm sorry, on the sides, I've got 200 square feet, and it's $1 per square meter on the sides. So this is going to be $200. Okay, so I know again I'm kind of running out of space, guys. I hope I'm not losing anyone here. This would be $100 plus $200 is equal to $300, which is good. That's what we wanted. It says, can the box be constructed for $300 or yes or less? The answer is yes. It would actually, if you had these dimensions in here, it would end up being exactly $300. Okay. So I know this question went one extra step further by asking you, can it be constructed by a certain amount? I don't think your practice problems are going to go that far, but if it does, just know that you would be taking your dimensions, right? These are your optimal dimensions, your X and your H, plugging them back into your area, and just seeing how much it would charge for the top, bottom, and sides. Okay? So I'm hoping this one example sets up a good example of steps that you have to go through to solve these cost problems on a square box. Your practice problems should be really similar to this. Please reach out to me if you have questions and let me know.